So on motor, if we send electricity through an electromagnetic or create an electromagnetic field, it will pull a magnet around. Yep, that's a what?
Electrical motor.
It's an electrical motor. So what happens if I take a magnet, though, and I put a magnet through a coil of wire? If I take a coil of wire and put electricity through it, I end up with a magnet. What happens if I take a magnet and put a magnet through a coil of wire?
Generator.
I get a generator. All right, so if you would, sir, please shake that back and forth, make that magnet move through the coil of wire. And what do we have on the end? We have a light.
Shake weight.
Got him in the eye. What we have right there is a generator. The magnet runs back and forth through that coil of wire, and it's actually generating electricity. So I can take electricity, put it through a coil of wire, and make a magnet. But if I take a magnet and put it through a coil, don't turn it off. Leave it on. No, it was on. Shake it again.
Okay.
Okay, it's on. So pass it around. See that magnet's going through that coil of wire, and you can see that we're generating electricity, right? How cool is that?
Let me ask you this.
Look, that's on the ceiling.
Yeah,
See?
I'm talking about, but in the dark, right? This ain't gonna help you.
It's not about practicality.
Oh, okay.
It's about knowing.
A real one like that you bought for the purpose of an emergency. I was like, do you never see any?
It's about a magnet running through a coil of wire, and that is creating electricity, which is the opposite of a solenoid. A solenoid is electricity running through a coil of wire creates a magnet. That's what it's about. Okay? See, through a coil of wire? It's got to go faster to make it a force. There we go. See, electromagnets. Right? Pretty cool, huh? It's not electromagnets. The opposite of electromagnets is now a generator. It's electricity. So that's just one coil of wire. But I can also do it another way. You have a gear reduction system. Now this is a different type of bulb. That's an LED. So over here in this one, I have a few windings right here. And I can take and turn a magnet inside these windings. If I turn it fast enough. But if I loosen the light's the load. And if I loosen the light on here and then try it again, turns way easier. If I tighten this bulb in here, you can feel the extra resistance. So what we have is you have the Hoover Dam, all that water's behind it, pushing against these turbines, and if there's a heavy load, more resistance on it. But if there's not a load, the difference? That's a generator. Has to do with coils of wire and a magnet. So let me make this a little easier to see. What we have here is coils of wire, magnet. This magnet is connected to this side, making all of this south or north or one or the other. And the opposite side makes the other one the opposite. So here I got a coil of wire running inside this electromagnetic field. Basically the whole outside's the magnet. As I run this wire through, see the light flashing? What kind of current do you think that is? Direct AC, it's flashing, alternating current. It doesn't matter which way I turn this, it's flashing. If I turn it to the DC side, which is using, the brush is using a different way of doing it. If I turn it, it's flashing and not, we're still seeing that magnet turn through there, but if I turn it the other way, nothing happens. I have to go one way. So what's cool about this, if that's not cool enough, is the light flashing? Pull the magnet off, please, sir. That's the light. So without the magnet, is it going to work? Drop that magnet back on, please. Magnet.
So if you turn the magnet around, it still works, though, right?
You can't turn it around, right?
get their hands on. Yeah.
DC would just stay solid?
Well, I can't turn it fast enough.
Oh, okay.
Pull the magnet off. Turn the magnet the other way. Well, I meant like. Still not on, right? So I have to go the other way because we reverse the magnetic field. Generator, opposite of a motor. Here I have the magnetic field around it. I put the coil of wire in it. I'm generating electricity. But if I send electricity through the coil of wire, I can make the magnet turn. Opposites, right? Pretty neat, huh? So what we can do is we can take say some big blades. When the wind hits the blade, the wind catches the blades and turns a shaft. That shaft can then turn either a magnet inside of inside of coils of wire, or turn a coil of wire inside of magnets. Either way, and we generate electricity. I can send electricity from power lines all the way right here, and take that, plug a fan in, and take electricity, and then put it from coils of wire, electricity through coils of wire, and make a magnet turn, and make wind right here from wind from someplace else. I can take photon energy from the sun. Solar, hit solar panels, have a reaction, convert that to electrical energy, take the electrical energy, run it in through these lights, and turn it back into photon energy right here in the classroom. I can take water, the Hoover Dam, that water running through, turning big turbines. Those turbines turn this, creating electricity. And I can take that and hook it to a pump here, plug it in, have that pump move water back the opposite direction right here in this room. I can take heat energy from a fire, take heat, burn fire, make that fire turn, put that heat energy in the water. That water can make steam. Steam can make a turbine turn. As that turbine turns, that heat energy is making electrical energy. I can take that electrical energy from that point, bring it all the way back here, and I can hook up my little steam generator, convert it right back to heat here, whether it be heating for cooking or the little steamer thing wherever I left it, and create steam energy or heat energy right back here in this room. Or I can convert those energy sources from any one of those to any of the other ones. Pretty neat, huh? All with this here. Pretty cool, right? They're all using some kind of a motor turning except for solar. The only energy we get outside of our planet is solar.
We get a lot of it.
We do, a lot of it. Very much a lot of it. So I'll let you guys use that the next break. It's just they make a lot of noise, and we pass it around, and it's making all this noise, and I can't talk, and I get angry. All right? Questions so far? Nope. Okay. So let's go back to our little toaster here. Oh, actually, we got something else to cover before we go there. Something else to discuss. To have a circuit, we need to have three basic things for a circuit. For a circuit, we must have a source. How do you spell circuit?
C-I-R-C-I-T.
Okay, if you say it's right, it's good enough for me. Circuit, we must have a source. So for me right now, for simplicity, it's the plug outlet. Of course, the plug outlet has a source, which is our breaker panel. The breaker panel has a source, which is the electric meter. The electric meter has a source, which is the transformer. The transformer has a source, which is the power lines. The power lines has a source, which is the substation. Substation has its source, which is Hoover Dam or a windmill somewhere or solar panel somewhere, or anywhere from there. But for me, the source is going to be that plug outlet. Or for a car, the source would be your battery, right? Or technically, it could also be the alternator. The source, we must have a source where we're starting from. We must also have a path. What do you think the path is going to be? Wire. The wire, yes. Wire. And we can also think of a path as being possibly a switch. Switch can be a path. We have to go sometimes through a switch. We'll get there in a minute. And we must also have a load. Source, a path, and a load. We must have those three things to have a circuit. A source, a path, and a load. So here I got my toaster, and I have a path here, and I have a load. My electric heat elements here is a load. Do I have a source? No, I have to attach it to the source, right? So it's not going to be a full circuit because it's not working. Sounds good? Well, a load is going to have some kind of ohms, some kind of resistance to it. And it's usually going to be what we want to make happen. So an electric heater or a fan or a light bulb or something that I want to work with. That's going to be our load. Whatever we want to take that electricity and convert it into something else, that's our load. Okay. Oh, and I don't know if everybody saw it, but here's a motor, a 1, 2, 3, 4, 5, 6 pole motor. You can see it.
So that's a solid one.
Yep. Let's talk about switches. Got 99 problems, but a switch ain't one.
Born in the country, we get one switch. Yeah, go to the switch. You always come with the smallest one too. You come out with the tree.
There you go.
How do you spell it?
S-W-I-T. T in there. Yeah, S-W-I-T.
Yeah.
Yeah. Like which, but with an S.
Got it. Switch. A switch can be one or two things. A switch can be open, or a switch can be closed. We can have an open switch, or we can have a closed switch. One of the two. Open or closed. That's it. It's the only option we have. Right now, these light switches are in the up position. What are those switches right now, do you think?
Open.
Oh, who said closed? What's with closed? That's exactly right. Yes. High fives. Cha! Absolutely. So when a switch is closed, that means there's a contact from one side to the other, and it closes the path or completes the path. So from this moment on, light switches will no longer be on and off. Light switches, when you flip a switch, are always going to be either open or closed. I want you thinking about that because it's going to help you through this class. And say it out loud when you do it. When anybody else turns it on in your house, they flip a switch. Ask me, hey, what happened to that switch? I turned it on. You say, oh, no.
Close.
That's a closed switch. Right? If you can't remember, pull up your notes. Closed switch. So let's think about this a little bit. We're going to start with an open switch. Right? So let me go ahead and open this switch for us, and then we'll take the rest of our notes. Oh, wait a minute. That may not be a great idea. What happened to this switch? What is this switch right now? It's open. What is it now? Closed. What is it now? What is it now? Okay, so let's think about what's happening to an open switch. The open switch, will it allow electrons to flow? No. So we're going to put here no flow. And by no flow, I really mean no flow of electrons. Will electrons flow? No. So if I open that switch and check voltage of the light bulb, what would the voltage show? 0 volts of potential difference. I have no voltage to the light bulb. If I have no voltage to the light bulb, will the light bulbs come on? No. So does it mean to replace the light bulbs? No. Find out where I lost power. So I'm going to follow the wire back until I get to the switch. I check voltage out of the switch. There's no voltage out of the switch. Is it a bad switch?
Yes, maybe.
Maybe, but let's see if there's voltage coming into the switch. Yes, there's voltage coming into the switch, and there's no voltage coming out of the switch. What's going on at the switch? The switch is open. That doesn't mean it's bad. It just means it's open. Now we're going to look see what position the switch is in. Oh, it's in the open position, and it's open. Oh, look, I'm going to flip it. Flip the lights. I fixed the lights. Wow. I need to just be thinking about this way, though. No flow of electrons. Okay, so if I have an open switch, a light switch, or any other kind of switch, and the switch is open, and I was to disconnect the power, isolate the switch, and I was to ohm it out. use my meter and ohm it out. What would the resistance be across an open switch?
0. Wait, resistance.
No.
Ooh, I'm getting different letters here. So let's take a vote. How many people say there would be 0 ohms across that open switch? Raise your hands.
Well, now.
1,
Infinite.
2,
That is infinite.
3. So 3 people say 0. All right. Who has another answer? Infinite. Okay, let's go with that one. How many people say that one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12, 13, 14, 15. Oh, who didn't vote? Neutral, okay. 1 for neutral. Neutral 1. And 2 for neutral. Hey! Who's got your back? All right, so that switch is open. So let's think about as if we were driving. Anybody ever driven in Miami before? All right, so when you're driving to Miami and you got to cross any of those bays over there, they have the ships have to go through. So if you're driving through, you have force, you want to get someplace, you have a path, but the next thing you know, the drawbridge opens and your car is right here, and those ships do not get in a hurry. It's like when that drawbridge coming up, you're like, oh, ship.
Gun it.
And you have to wait. And you sit there. Now, do you want to flow?
Yes.
If there's cars behind you pushing and wanting you to flow, can you flow?
No.
What's the resistance between you and getting to where you need to be?
0. Infinite.
Infinite resistance.
Because it's like the ball.
You have infinite resistance. There is no possible way you're going to get to where you want to go. Even if people start pushing against you, there is no way for you to go. You have infinite resistance. So the answer is infinite.
I remember from you smashing a ping pong ball on the table.
Yeah, that's
So an open switch will have infinite resistance. What's the resistance between you and the moon? Infinite resistance. There's no path for you to get to the moon. Infinite resistance.
What
All
if
right.
you ask that question to someone else, like
Yeah, it's wide open.
Neil Armstrong?
Well, Neil Armstrong's not here, then is he? Took a page out of his book.
I'll see myself out.
See you tomorrow.
Now, a closed switch. Now, that drawbridge closes. Will we have a flow of electrons?
Yeah.
Yes, they will flow. Yes, there will be a flow of electrons. What would the resistance be?
0.
0. 0 resistance. 0 resistance. What's the resistance between you and the chair?
0.
0. You're touching the chair. There is nothing stopping you from touching the chair.
Oh, okay. Round, that's how we keep it.
Stand up from the chair and then just let go of your legs and see what happens. What's the resistance between you and the chair? You go right to the chair. It's like every time. There is no resistance between you and the chair. All right? So a closed switch will have 0 resistance. Yes, it will flow. An open switch will have infinite resistance, no flow. Now, these words are tricky. The only way you're going to start learning these is, studying them. Make some flashcards. Study them. And it's a must that this gets into your head, because this is how everything's worded in HVAC. The switch is open. The switch is closed. What's the resistance between an open switch? Infinite. What's the resistance of a closed switch? 0. If you get a number other than that, then there's going to be a problem. So now let's go to my toaster. What do you put in the toaster?
Bread.
You guys still are awake. I'm impressed.
Frozen chicken breast.
A horse. A horse will not fit in here.
Fork in there.
No, that will fork it up.
It already looks pretty good.
That's what I was hoping you would say.
That's why. See, look, you brought that home. It was like, no, what do you mean we have a toaster?
The X is like, have you seen the toaster?
What's a toaster?
Yeah.
I can't see the toaster.
Oh, man.
I didn't ask if you could see it, but have you seen it? Oh, yeah, I've seen it. It used to be in the kitchen. So now she's on to me, because I can't lie, right? Where is the toaster? I prefer to plead one of the amendments.
Yeah, please.
I don't remember if it's the one to own arms or the one I shouldn't say anything. But
Yeah.
one of both of those at this point. I'll take both of them.
Yeah. I like to vote both.
So, I don't think she wants it back.
I think so.
But there's so much HVAC in this toaster. It's great.
Yeah.
I got my path here. If I plug it in, I'll have a source, but I have a path here, right? Here's what's cool. Look right here. See that little flopper right there?
Yeah.
What do you think those are right there?
Little flopper.
Well, this is the
Baby
flopper.
floppers.
These metal things.
I love the little flopper. That's
Right? The wires connect to it.
Oh, it's your contact.
Oh, it's contact. It's a switch. The switch is normally open, and if I push this down, the switch closes contacts. As it closes contacts, it allows for a path to continue on to the heat elements. It's a little contactor. Say hello to my little contactor. It is a little contactor, right? You see it? So when I press the lever down, when I put the bread in there and press the lever down, there's a little switch right there. It's normally open. But when I push this down, it closes those contacts. You can even see the contacts close. How cool is that? There is a switch in a toaster. See how the switch works? Pretty neat, huh? Right there, a little switch. It breaks both legs. It's actually called a double pole switch. So the switch is open, it's closed. Now it's open, now it's closed. Now it's open, now it's closed. Now it's open, now it's closed. Open switch, closed switch. Open switch, infinite resistance. Closed switch, no resistance. Open switch, infinite resistance. Closed switch, no resistance. Neat, huh? So there is a switch. It's a little contactor inside of here. It makes contact. So when I push this lever down, there's a little mechanism over here that locks it, that holds it down. And it allows this switch to close. So now electricity can flow through the switch, and we have a full path going to our load, which is our electric heater. And it will start converting electrical energy, watts, into heat energy, BTUs. Neat, huh?
taking heat from over here and putting it over here.
So how does it know when to pop up?
Oh, that's a good point. So it has a point that says one slice. When you put the bread in, there's a little piece of metal. It's called a bimetal. We'll get there later. But a bimetal, when you get it warm, it starts to heat up and it starts to warp. It starts to bend. There's two pieces of metal, two different metals. One metal will warp faster than the other metal. So when I heat the metal up, one metal bends a lot. The other metal bends slowly. And it starts to warp. So the metal starts to do this. I can't. Here.
Yeah.
Right? So it's like this. As I heat it up, it starts to bend like this. What it does is it bends. It pushes a rod that's connected to it. And that metal is energized electricity. And as it bends, it starts to push a rod. That rod pushes over here on this side. So on here, I have a little lever. If I put the lever all the way this way to the lighter color, this next piece of metal is very close to that rod. But if I move this lever the opposite direction, it pulls it very far from that rod. In other words, if it's over here, the metal has to warp just a little bit to push the rod over here. And if I move it to this other side, the metal has to warp a very long ways before it touches over here. But when it touches over here, now I have a path over here to an electromagnet. There's an electromagnet right here. This little electromagnet then will energize. And when I energize an electromagnet, which is basically a solenoid, it pulls this piece of metal. And when it pulls this piece of metal, it releases the lever and the springs pull it back up. And then when the springs pull up, it also allows the switch to then open, shutting off the heater. Pass it around. Play with it. There's HVAC in a toaster. Seriously, there is. Next, I want to take those components out and rearrange them.
Yeah.
Yep, I'm going to take that contactor out and make a remote contact like what we use.
How are we going to make toast?
Not. We're going to hook a fan to it and make it a heater.
We're going to need that in the next couple weeks.
Yep. Will we?
Oh, yeah.
Is there a cold front coming?
We're going to need it.
Hey, see,
What do you
that's the
mean
truth
cold?
right
I don't know
there.
what's
Oh, yes, he got me. Yes.
I got to make up for that other one from 4 or 5 classes ago.
Good. But you got to think about what's happening with the switch. How it's connecting, how it's locking in. Does it make sense? Do you see it? You have questions yet? No?
I
None?
really never cared about what a toaster did, and now it's like, now that I know, it's.
The new
I can't
ones
just stay
have
and
digital
stand there and
controls.
stare at it and watch it, but
The new ones have digital controls. The old ones are like that. They work great. I mean, it's just tons of electricity, HVAC, all kinds of stuff, all in that toaster. It's fantastic. It's awesome. What's that?
Thank you for borrowing her toaster.
I know. She did such a great benefit for all of us. All of your
I can just imagine if you
education.
left it on the counter like that. Like, all I see is this weird metal box thing.
Well, of course I did. I had to bring it back. She said she wanted her toaster back, so I brought it back.
Unless you didn't want it back.
Then she started calling me by a different name that I prefer not to repeat.
Ah, yeah, you know,
So I had to go buy her new toaster.
more of a tribal name.
So
I mean,
You buy her a nicer toaster?
and a new hair dryer.
out of curiosity. He just gave her a
and the steamer and an iron. Yeah.
half your paycheck.
Not the metal, well, not the outside metal frame, but if I touch the inside where the heater elements are or the wires in the side, then I will get a nice shock.
That's why they say
That's correct. Yeah, because if you touch that metal with a knife or anything, electricity's going through you, and you will get shocked. Yeah, I do not recommend taking them apart. This is only for educational purposes. Please do not try this at home.
All right, I'll try it at someone else.
Yeah. You tried it at your house. Can I come over to your house?
Anybody's home. But we're going to be doing more with that later on. But it's great to show. You get the switch, you get the electromagnet. There's bimetal, which is a control, source, path, and load. I mean, it's great. It's awesome. So questions yet? Absolutely, it does. I just need some bread. I don't have as much bread since I started teaching.
Nah, part of that sandwiches today. Yup. There's bread here. I know there is.
All right, questions? Any questions at all? I'll make sure I cover everything from the morning class. We got one more big thing we got to cover, and we also got to redo superheat and subcooling to make sure you hadn't forgot.
How does speaker wire work when you send electricity? Does it also like?
It knocks an electron off of one side to the next wire, to the next, all the way down that wire until it gets to where it needs to go.
So the signal would be considered electricity as well?
Yep. It is pulsing. Now, what does it go to when it hits the speaker? Do you know what it goes to at the speaker side?
Voice coil? So the coil?
A coil of wire, which is an electromagnet. And what else does the speaker have in it? A magnet. Aha! Right? So now you have an electromagnet and you have a magnet, and we send the pulse in. The electromagnet then wants to push away, right?
Yeah.
And come back, and you send the pulses at different amounts. You make different movements, you make different frequencies, and as you have different frequencies and different pulses, that's then moving the air, and the air is doing like this. Molecules are bouncing off the air, in which case makes different sounds, in which case our ear picks it up, and we hear that as being, in some cases, music.
That's that big.
Bigger magnets, they want to really push a lot of air, and that lot of air, when you're feeling that bass, you're feeling that a lot of air. Yep.
The bigger the magnet, the better for a subwoofer.
Right, yeah, that's right. But it all goes into electricity, electromagnets. Now, you're dealing with DC, and you're dealing with some other things that go in with that we haven't got into. But yeah, it flows that same way. And it's not just the size of the magnet you want to look at, but also how many, the size of the wire on there, how many amps that magnet can handle, how many wraps there are on it. I mean, there's a lot going into that.
It's not always the size of the magnet that counts.
That's how you use it.
So RC cars, when you use the electric motor in an RC car, they count the power by the amount of turns. And the less turn, I don't know if this is the newer ones or the older ones, but the less turns it had, the more powerful the motor was.
That's right. So let's think about that.
It always baffled me, so I don't know.
If I have an electric heater and it has less... Actually, before we get there, let's do this first. We're going to circle right back to
We
that.
still got an hour and 15 minutes.
Ooh, I'm running low on time then. All right, so formula for watts. Watts is what? Electrical power. So if I take the amps and I multiply it by the volts, I will end up knowing the watts. Or I can take I, multiply it by E, and end up with P for power electrical. That's the formula for power. Not just the amps. A lot of people are like, well, how many amps is that pulling? Well, if really amps alone is irrelevant without the volts. Well, geez, I'm pulling 6 amps. Is that a lot? Well, let's check the voltage. Okay, I got 12 volts at 6 amps. 12 times 6 is what? 72, right? So I'm pulling 6 amps at 240 volts. 6 times 240. 1440? I don't know. A lot more. A lot more, right? So people are like, well, what's the amps on it? Well, the amps don't really matter if you don't associate that with the volts. Amps times volts is what? You need to know how much power you're using. You got to know both. It's a big factor on that. A lot of people don't see that. So you have to have the amps and the volts. Multiply that, you get the watts. Amps times volts is watts. It's another formula you're going to have to learn. That and this Ohm's law formula. Got to know. Okay, so now we understand volts over resistance over amps. Let's go back to your question. So let's say, and I'm going to break this into electric heat. Let's say that I have, on volts, let's say I have, we'll use 120 volts. And let's say I have an electric heating element. And the electric heating element has a resistance of 10 ohms. How many amps would that be pulling? 120 divided by 10 equals 12 amps, right? Now, if I know my amps are 12 amps, and I know my volts is 120 volts, how many watts of energy would that be?
144.
144?
Actually, 1,440.
1,440? Okay, that helps me give me the right number. 1,440 watts. Sound good? That's how many watts of energy I'm using. So let's think that I have a higher resistance. Let's say that we end up with a heater, and this heater has 20 ohms, right? Let's do the math. 20 ohms, bigger heater, right? Sounds good, huh? Let's do the math. 120 divided by 20 equals 6. All right, so that's going to change the number over here. So 6 times 120 equals 720. Wait a minute, I upped the resistance. What did it do to my watts? My watts dropped. And let's convert that to heat. We want heat, right? So my original number is 1,440 times 3.413 BTUs for every 1 watt. What was my original number of BTUs?
Oh,
Yeah, no.
4,914.
So originally I had 4,914. My new number is 720. So let's take 720 times 3.413.
62. No, 720. It's 2,457.
So that's less than half of my BTUs, right?
It should be about the same because you cut 12 because before it was 12, now it's 6. So it's just
Yep, pretty close right there.
pretty much half.
So by increasing my resistance, what did it do to my amps? Dropped. Now less amps equals on the same voltage. Less amps means less watts. Less watts means less heat. Means less heat. So if I have a inductive wire and I have fewer wraps of wire on there, fewer wraps means I'm going to have less resistance. Less resistance is going to be more amps. More amps is going to mean more watts, right? You see how that's working? So it's all about the resistance. Now I can still have more wraps of wire if I compensate with something else, whether it be the wire size or things like this. There's other ways you can do it. It's not about just simply one number. But on a heater, the less resistance you have, the more amps it's going to pull. When you get to big commercial equipment, like, wow, big commercial equipment, those a lot of times will have more resistance because they have more voltage coming into them. So they'll have higher resistance on them to compensate. I have this little electric toaster right here. It'll have a very low amount of ohms on it. The ohms will be very low because there's very little pressure. But if I take that toaster and I plug it into the lab where we have 240 volts, a lot more push on that same resistance, electrons going to flow faster? Yes, the electrons will flow faster. that wire size can't handle the faster current, right? The river can't handle the faster flow, so the wire size can't handle that faster flow of electrons, and the wire will overheat and it will catch on fire most likely. If you don't believe me, bring your toaster up here, we'll try it. Questions so far? Does that answer your question? Get your minds without going into big detail. You're thinking about resistance will affect the amps. Amps and volts gives us the watts, and watts is our energy usage. Yes, sir. Very high amount of voltage, a lot of pressure, a lot of push. So the next thing is, what's the voltage? What size batteries do you put in a taser, right? You got a small amount of voltage, but the voltage coming out is a whole lot higher, right? So the real question is, how does it take a battery voltage and step it up to this really high amount of voltage?
Little resistance.
Transformer.
Yes, transformer. So right here, I have taken 120 volts, and I have used a transformer to drop the voltage down to a lower voltage. I could go it backwards, and it will take lower voltage and step it up to higher voltage. So let's talk a little bit about that. Just briefly. We're not going to go into a full class on transformers. We're just going to briefly discuss it. What do we need for a circuit? Source, path, and a load. An open switch has how much resistance? Infinite. A closed switch has how much resistance? Zero. Good. So if I take a wire and run it into a coil, and then I take a metal rod and I energize this electrical wire, what's going to happen to this metal rod? It's going to become an electromagnet. Yes! Electromagnet. That's exactly right. It'll become an electromagnet. 100% it will. What would happen if I take a separate coil of wire over here You know what? Let's do this.
We appreciate that, though.
All right, now I have this electromagnet, and now this electromagnet is running, and it's alternating current, so that magnet's changing direction 60 times a second. That magnet is now running inside of a coil of wire. What's going to happen to this coil of wire?
It's going to be energy. It's going to take the electron.
Can you grab the flashlight? Can you run that magnet through that coil of wire? So if I have a metal rod that has a magnet that's changing direction 60 times a second, and that magnet is running inside of a coil of wire, what are we going to create?
Power.
Create voltage. Another currents, right? We're going to have electricity is called induction. It will induce a magnetic field. That magnetic field will then induce a current into this coil of wire. All right, thank you. Pretty cool, huh? It is. So here's what's really interesting. If I have the same number of wires here and the same number of wires there, whatever voltage I have here, well, I'll have that same voltage over here. Which works great in, say, audio systems. They do this because I need 12 volts in and need 12 volts out. But what's beautiful about this is as it goes through that magnet and back out the other side, it helps smooth that energy out. It takes out some of the roughness in it, some of the pulsations maybe in it, helps smooth that out. And so by doing this, you get a cleaner power coming out the other side. It's an isolation transformer. Helps clean up that energy, keeps it smooth. Takes out any other kind of signal that may be in that wire, helps clean it out on the other side. But, wait, that's not all. If I have fewer wraps of wire on this side than this side, it's going to pick up it's going to induce a weaker current into it. So I can have high voltage here, and if I have fewer number of wraps here, I have a voltage drop. I can step the voltage down. Or wait, if I put more wraps of wire on this side, I'm picking up and inducing a higher voltage on the other side. So I can take my voltage and step it up to a higher voltage. So a taser has a battery with a very small amount of power source here, and we then have a few wraps here and a whole lot of wraps here, and I've taken a voltage from a very low voltage to a very high amount of voltage, and voila, I have a taser, which disrupts your electrical system, which then makes people pass out and their muscles release and things happen, and they fall on the floor.
And your resistance to the floor is infinite.
No resistance to the floor.
Yeah, the opposite.
Zero resistance.
Opposite, yes. So that's how a taser works because of a transformer. It's stepping up the voltage. Now here's the thing. A lot of you go like, how do you create more voltage? Well, what's not changing is watts. The watts has this, and watts is electrical energy, right? Or watt stays the same. Or watts is not changing. So, not changing. Or voltage changes. So let's say that I have however many voltage in. Let's say I have, let's say watts. Let's say I have 100 watts in. I will have 100 watts out. So let's say our battery, let's say we have a 12-volt battery in there. So my watts is 100. I have 12 volts over here. Well, let's do it backwards. My watts is 100. What's the opposite of times? Divide. So if my watts is 100, my volts is 12, what will my amps be? 3.3 amps. So I'm using 12 volts, 3.3 amps.
8.3.
Oh, 8.3. I'm getting older. You gotta get well louder. So over here, my watts, let's say I have 100 watts, and let's say I want 100 volts. So, yep, we'll do that. So 100 watts divided by 100 volts is how many amps? 1. So my watts, my volts went up to 100 from 12 to 100, but my amperage dropped down to 1 amp. But 1 amp's not good because that'll kill you, right? So they'll step it up even higher. Maybe it's 1,000. So let's do it with 1,000. So what is 100 watts divided by 1,000 volts? Less. You're doing it the other way.
10.
It won't be 10. Put it in your calculator the right way. 100. Put in 100 first. Then hit the divide sign. Then hit 1,000. 0.1. So now I have 0.1 amps. Did my watts change?
No.
I still have my watts. I cannot change my electrical energy. But by pushing it up to a much higher amount of voltage, I end up with much less amperage. So at 0.1, we're most likely not going to kill somebody. But just to make sure, okay, we'll step it up maybe at a higher amount of voltage. More racks, which means it's going to have even less amps that it can handle. It's amps that kill you, right? Yeah. So I want to make sure I get this amps number down as low as possible. We can step the voltage up. It's gonna hurt. It's gonna hit. You're gonna feel that pressure as it flows through you. But we keep the amps down low. It's the amps that kill you. So a taser wants less amps. Does that answer your question? Yep. Bam! There it is. On the power pole, we have an extremely high amount of voltage, and what we do is we step that voltage down. Reduce the voltage, but the amps are going to go up. Transformers. You have transformers. In the lab, we have transformers that step it from a higher power down to a lower power that powers this building, right? And they're disguised around metal cases, so you don't see it. But so they're just robots in disguise. Right? Here's one right here. Look, it's a transformer. See, it's got this metal and plastic around it. It's kind of disguise it, but if you take that disguise off, you're going to see the transformer. It's going to be wraps of wire. You're going to see the robot right there, wraps of wire. Transformers wrap. Yep. Coils of wire. More coils on one side than the other. Thick amount of wires, fewer amounts of wires, right? It's stepping it from one way to the other. I wonder if we pull that disguise off, if we'll see their symbol. We can see if it's what's happening to it. So sometimes when you're working over here, notice how I have it going through a fuse to protect it. But if I took that fuse off and I shorted one side to the other side, would there be anything slowing down the flow of electricity from here to there? No, it's going to happen to this transformer if I don't have a load. Like here, this is my solenoid, it's my load. What if I connected the low voltage side straight to each other? We would have a short circuit. what would that do to the wire right here? It overheated, it'd burn it up. What would happen to my transformer? It'd be bad, right? It turns a transformer into a Decepticon. A bad transformer, right?
Into a Michael Bay movie. Oceans everywhere.
By having a short circuit. Instead of something happened, instead of going to a load, whatever that load is, something happened and the wires touched, and the electrons went from here straight back there. We had a source, we had a path, but we did not have a load. That's called a short circuit. They made movies about that. I think there's 3 of them, maybe 4 of them.
Yeah.
Johnny was his name?
Yeah.
Johnny 5. Short circuit, right? But electrons take a shortcut, a short circuit. It's not making a full circuit, it's making a short circuit, not going through the load. Just like trying to run with the scale, running as fast as you can. There's no load, there's nothing to slow it down. You have a short circuit. It's going to overheat those wires, it's going to burn them up. Where's that motor that we passed around? There we go. Yep, this motor right here. All right. What's on this right here? What do you see right here?
Wires.
You see the number of poles. You see wire. Now, what am I touching, though? Now, yes, there's no energizing. There's no flow of electrons. I'm touching the wire? Well, actually, I'm touching insulation. There's varnish on this. It's clear. Right? It's clearly varnish.
Is that the brand name?
It's the insulation over here. It's the color is black over here. There's no color. Right? It's clear. It's varnish on there. So what happens if I overheat this wire? That varnish will overheat, and as it overheats, it will cook. It will melt. It will actually catch on fire, and then the smoke's going to come out. Once you overheat this wire, the factory smoke comes out of the motor, and once you release the factory smoke of that motor, you cannot get the factory smoke back into the motor, and it doesn't work anymore without the factory smoke. Once you let the factory smoke out, it doesn't work anymore. I'm serious. You short this motor out, the factory smoke's going to come out of this motor, and it won't work anymore. And I haven't figured out how to get that factory smoke back in it. Some of you in this class, before we finish this class, are going to release the factory smoke from one of these parts. And you will know what I'm talking about. So far, so good?
Yeah, so what makes a transformer blow up then? You know, like...
A short circuit.
Oh, so that's what we do then, yeah.
And electrons flow so fast, there's nothing to stop them. They're running through that so fast, unrestricted, nothing to stop. There's no load to slow it down. So the electrons are flowing so fast, it starts to create heat. And as the electrons are flowing so fast, there's nothing to stop it down. It gets hotter and hotter and hotter until the varnish actually catches on fire. When it catches on fire, it releases the factory smoke. Won't work anymore.
And then there's a massive... And so
It smells horrible. Horrible. Yep.
That's why you don't give a kid a Red Bull.
So the fuse is considered the load, right?
Fumes?
The fuse.
Oh, the fuse. No, the fuse is a protection device. As electrons flow through that fuse, it's the weakest link of the whole thing. So electrons flow too fast to the fuse melts. The fuse melts in a safe area, and when the fuse melts, it opens the circuit. Infinite resistance electron flow. Electrons cannot flow. We've protected anything else on that circuit. We've prevented by having the fuse melt. The fuse melts way before the transformer melts. So we keep it as being the good transformer. I don't remember what the good one's called. The Autobahn. There we go. Autobahn, whatever it is.
Both of them could work.
I made an Autobahn.
All right. So far, so good? All right, before you touch the electrical circuit, you must make sure that there is no potential for you getting shocked. So I'm going to set my meter to potential. How do I set it to potential? Volts. Yes. John Volta. Tra. So I'm going to set it for volts. And what we want to do is we want to check all the lines. Line 1 to line 2. If there's 3 lines, line 1 to line 2, line 1 to line 3, and line 2 to line 3. If there's 4, we check all 4. However many there are, you check all the voltages to all the possible scenarios. Then, you want to check line 1 to ground, the actual casing. Then you want to check line 2 to ground, line 3 to ground. You want to check every possible scenario before you touch it. You want to make sure there's no potential for you getting electrocuted. So we're going to go to the lab right now and do this. Check all these scenarios. I'm going to show you how to do it.